going to be an interesting ride from here on out. No, interesting in the truest sense of the word, not interesting in a sarcastic way. Right? So I realized a long time ago that just about everything I say comes off as sarcastic. Sometimes, believe it or not, I'm actually being serious. So, or at least not sarcastic. So finding parametric equations to represent a line. That's really what our goal is here. And so you might look at it and say, well, why do we need to do that? Why do I need to write the equation of a line parametrically? Right? And the short answer is because I said so. No, it's because y equals mx plus b doesn't work in 3 space the way it does in 2 space. All right, so what I'll do here, just so I don't have to deal with that nonsense associated with the touchscreen, I'm going to bring up Geogebra on my laptop and show it to you that way. All right, so I'm going to stop this share. I'm going to start that share. Here's share everywhere. Share. All right, so here's Geogebra. I entertain myself sometimes. I don't like the plane. It looks ugly, so I'm going to get rid of that. One of these days, I'll figure out how to make these settings permanent, but I never bothered and I never remember. And here I am doing it again. Get my X, Y, and Z's to show up just so I can know what I'm looking at. All right, this will be pretty quick because all I'm going to do is show you that if I type in a linear equation like y equals 3x minus 2, that ain't a line. All right, the reason why is, and I'll just make a little note here. All right, by the way, if you want to make a little note in Geogebra, just open a set of quotes and it'll let you type in a note without that becoming a string or I'm sorry, a set of variables. So it will be strings. So what this will give us is the relationship between y and x for all z. All right, and see, I typed it in and it disappeared. Just click on it, it brings it back up. So that gives us a relationship between y and x, but for all values of z. So if I give it a little top-down view and reorganize it a little bit, top-down view gives me a perspective that makes it seem like it's an XY coordinate system, all right? But it's really not, because there's the Z axis, it's just hard to see, all right? But if I change the perspective a little bit, you can see that that is the line y equals 3x minus 2, but with an infinite amount of height and depth, all right? So that's really what's going on here. And so I have my little label there that shows that this is really just giving us that that and only that relationship, all right? So you might say the same would be true for like a horizontal or a vertical line. Well, horizontal and vertical line aren't lines anymore, they're planes. So for example, y equals 2, all right? That's normally a horizontal line. Let me turn off this bad boy. If I look at that again from a top-down view, it takes a little doing to make it look nice, but top-down view, that looks like a horizontal line, y equals 2, but again, it's got some depth to it, right? That you don't necessarily pick up on until you start, playing around with it, all right? Yeah, that's really it. So we need another method to come up with the equation of a line, right? And so parametrically is the only way that we can do it, right? While I'm here, I figured, that IJ stuff that I said I would look back at again later. Well, let's make now later. So let's say I have the coordinates A equals 1, 0, 0, B 0, 1, 0. This is really more for me than you. I just need to have the personal satisfaction that there isn't a complete, a room of people who think I'm a complete imbecile because of the technology stuff. If you think I'm a complete imbecile, it's got to be for other reasons than that, right? So cross, and then you just type in your two vectors, A, comma, B, right? And then it gives you that result, and then you can just say vector. All right, so like I said, it's a whole lot easier than the way I was making it seem before. They're really small, so you might want to bring it in and take a look. Some of them, they pop out a little bit more than others, but they're all there. So all on the axis here. There's one. Oh, I never plotted vector A and B, but you get the idea. I could do it though. Because it's so much easier with a keyboard. So, yeah. So you could see that they're definitely orthogonal to one another, right? And you can tweak it around. So before, when I was trying to like contort my hand in order to get that right hand rule to work, if you're doing it on a laptop with a reasonable size screen, or even just a regular desktop, you can manipulate the diagram to fit your right hand. Right. So just a thought. Right. But anyway, that's really what I was trying to get across before. But bottom line is, we got a need, or we have a need. Right. And that need, it's to figure out how we can write the equation of a line in 3 dimensions, well, and beyond, because we're just kind of making our first foray into n space. Like we were living in 2 space, now we're branching out into 3 space. But before it's all over, we're going to look at 4 space and 20 space, and so what do lines look like in that context? It gets more and more interesting as we go. All right. So what I'm going to do is I'm going to plot an arbitrary point that we call point XYZ, and X sub 0, B, Y sub 0, Z sub 0. All right. So basically we have 2 points, point P sub O and point P. All right. So I'm going to plot those in space somewhere. It doesn't matter where you put them. All right. So I'm going to put point P sub O over here, and I'll put point P over right about here. Again, doesn't matter where you put them. All right. So this is going to be X sub O, Y sub O, Z sub O, and this is your classic XYZ. I'm going to connect them with a line segment, but it really is at this point just a line segment. Later on, it'll be an actual line. All right, so that's a line segment connecting those 2 points in space. Now, the deviation between those 2 points, subtract the corresponding components. We could find distance, same general idea. Those deviations squared, added together under a radical, all that stuff. We've been there. Now it's time to kind of bring it to the next step in the process. All right. So process to find the parametric equations for the line L that contains the given points and is parallel to the given vector ABC. Use the fact that the displacement vector between the given point P sub O and the arbitrary point must be parallel to V. All right. So let's do that. First off, let me grab this line segment and basically manufacture from that a parallel vector that we're going to call V. All right. That V is going to have components A, B, and C. All right. Now, something else to keep in mind, these 2 points, P sub O and P, are living on a line. This is a line segment, but it's part of a grander conspiracy. No, it's part of a bigger line. that extends off infinitely in either direction. Just going to kind of, it's one of those snapshot bad boys. All right, undo, undo. Let me just try to do that again using a technique I like to call the right way. All right, so this is really the line that we're looking at. Yeah, it's a little bit off, but we'll live with it. It's better than it was looking before. Because what it looked like before was straight up trash. Just trying to make it look a little nicer. All right, so that red line that we'll call L, that's what we're looking to find the equation of. And what we're going to do is we're going to invent a process here. Because you already have the formulas. Formulas are right below. Parametric equations for a line in 3D. You can see they have a linear kind of component to them. Or, well, they're all components, but the components have linear components, if that makes any kind of sense. So we're looking at the displacement vector P sub O and P. That's going to be parallel to vector V. All right, so what we're going to do is we're going to come up with that relationship, and that is that the line has to have a displacement vector P sub O P, which is going to be parallel to V. Now, that doesn't mean that it's going to be exactly equal to V. It just means that it has to only differ by a scalar multiple from V. All right, so it could be twice V. It could be 10 times V. It could be half of V. It could be negative 1/2 of V. All right, any possible scalar multiplier. So we're going to let T be the scalar multiplier. The reason why we select T is because this is eventually going to be parametric, right? And typically we use T to represent time. It's not always time, but it's our standard. It's generally what we go with, right? Now we also know that P sub O and P, those displacement vectors, those are going to be the difference between the corresponding values that make up those vectors, right? So we have P is X, Y, Z, and P sub O is X sub O, Y sub O, Z sub O. So the subtraction of corresponding values is going to give us the displacement vector that we're looking for. So X minus X sub O, Y minus Y sub O, Z minus Z sub O. That's going to be equal to T multiplied by ABC. All right, because we're looking at a scalar multiple, we can distribute it through. So in order for these two vectors to be equivalent, each component needs to be equivalent. So I have X minus X sub O is equal to TA. Now, if I want to solve for X, because I am looking after all for an X component, when I'm talking about a parametric equation, it's X comma Y comma Z. In 2 dimensions, it's X comma Y. All right. So solve for X. This gives me X equals X sub O plus TA Or I could say TA plus X sub O. All right. And the same would be true for the others. I don't know that I need to waste your time writing it because it's just going to amount to the same thing. And it's all written for you anyhow. So it's just a matter of how you prefer to write things. You know, I kind of have it in the two schools of thought. One is the way that you've probably already seen it is y in the form of y equals mx plus b. So you have your slope, you know, you have your variable, and then you have your constant value, right? But then there's also the idea that if you're looking for the equation of any kind of linear function is usually a fixed quantity and then some variable quantity. So why wouldn't you start with the fixed part of it and then build off from there? You know, so if I tell you that, you know, like I'm starting a new job, I'm going to make $50,000 a year, and they're going to give me a $10,000 signing bonus. I'm gonna take my $10,000. I'm starting off with that, then add to that $50,000 multiplied by the number of years, right? So what I'm starting with, and then the variable quantities after that. So that's kind of the school of thought that leads to this set of parametrics to give us the equation of a line. This one right here. But because we're kind of living in the world of vectors, you know, we had a whole unit on parametrics and polars and all that stuff. Now we're kind of living in the world of vectors. What's the difference? Well, just how we represent it. Now, a vector quantity is going to be in the form, or the component form anyway. You know, you could put it in IJK notation if you want, but I think it gets a little ugly when you do it that way. So we can write it as X sub O. I know some people say X null or X naught. I say X sub O. I know it's not an O, it's a 0. It just rolls off the tongue a little bit better for me. So that's what I mean. So if you're familiar with the other way of saying it, that just know that I'm talking about the same thing that you always knew. Right. Y sub O plus TB, Z sub O plus TC. For the symmetric equations, let's actually get rid of that and write it as IJK form. Because honestly, I'm never going to ask you, and I'll take this as a typo. I'm never going to ask you to put it in symmetric form. So it's not, there's nothing wrong with this information. It's useful. It's just we're not going to make use of it. Right. So the IJK form, like I said, it's going to look a little uglier, but it's fine. And we will make use of it, just not today. The satisfying sound of typos coming in. All right. So in the IJK notation, all I'm doing is I'm just tacking on an I, J, and K to each component and adding them all together. All right. Either way, what we're looking at are what are known as, and we'll formally discuss this more as we go forward, but these are known as vector valued functions. All right. So they're functions that are valued in terms of their vectors. All right. So that's really all it is. We could have actually written, if you go back to the first unit, geez. That's a misspeak of a lifetime. the first math class, first real math class you ever took, you know, involving algebra, that's where you could go back, like the linear equations, or even you know, basic polynomial functions, things like that. Those could all be written as vector valued functions. And so we're going to learn some calculus and you know, both differential and integral calculus related to those concepts. So there's a lot of good stuff coming along the way, a lot of interesting stuff, and applicable stuff. Hopefully you'll agree with me as we go on. So in the same vein as the typo that I just identified, symmetric equations, we're not going to bother with those. So let's get rid of, I say a lot. Let's get rid of the and symmetric part of number one. All right, so another typo for somebody. All right. So find parametric equations of a line passing through 1, 4, -2, and -3, 5, 0. All right. It's really not that bad because we have a process that we can follow. You just got to know what the question, or I'm sorry, no, I was going to say what the question is asking you to do. That would be the understatement of a lifetime. What each thing in the question is related to, right? So we have in our initial setup an x sub o, y sub o, z sub o. That's a starting point, and then we have some variable point out in space, right? That's something that's going to have to be built into our equation. So I don't want to be plugging anything in for x, y, and z. Those are the things I'm solving for. All right, they'll be solved for x, y, and z in terms of t. So I want to leave t variable. So I really need two pieces of information. I need x sub o, y sub o, z sub o. That's one piece of information. So that corresponds to some point that we know is on the line that we call p sub o. Then I need what we call the parallel vector, vector v, which has the points a, b, and c. I'm sorry, components a, b, and c. So just like when you're writing the equation of a line back in Algebra 1 or college algebra, when you're working with the 2 points that you were given, you could choose either of the 2 points to work with. It didn't make a difference, right? So what I'll do is I'll just let this first coordinate, I'll box it in. I'm going to let this be equal to p sub o. So if you wanted to, you could let the other one be p sub o. You'd get a different looking set of equations, but they would amount to the same thing, right? So this would be 1, 4, -2. Now my parallel vector, ABC, right? So that's going to be the difference between p sub o and some arbitrary point in space, all right? So I can call this other point, I can call it p, but that might lead people to think that it's coordinates x, y, z, which I don't want people to be thinking about. So what I'll do instead is I'll call it p sub 1. All right. So we're going to let ABC, vector v, be equal to the displacement between P0 and P1. I mean, if you're thinking along the lines of physics, usually you use a subscript of O to start and an S subscript of F to end. You know, the time t equals 0 and t equals F for final. But here, what we're saying, like, this is my second point, right? So I could say point 1 and point 2, but if I'm pinning that first point as my origin point, not the origin, but the origin from my perspective, like I'm at that point, the origination of the line segment, then the first point that I care about, just thinking in terms of the ordinal number 1, that would make sense as the first point beyond my start. All right, so that would give us the ABC values just by finding the displacement between the two. All right. So -3 minus 1 is -4. I'll actually write the subtraction there so you have good notes. Good notes on good notes. So -4, 1, 2. All right, so those make up my A, B, and C values. So a good question at this moment, especially if I were in your position, would be, wait a minute, how do I know that that's A, B, and C? Like, I know that the displacement here has to be parallel to A, B, and C, but how do I know that that's A, B, and C? The short answer is it doesn't matter, because the value T will allow for any set of multipliers related to A, B, and C. All right, so if T is 1, then these values will be what they are. If T is equal to 20, then it's going to get scaled up by 20. Right, so as long as this vector falls on the same line as what the true vector ABC is, we can use these numbers. All right, so I now know everything I need to know in order to write the equation of this line. I'm going to trim down the size here. So it's either the vector form. I would stay away from parametric form, where it's x equals y equals z equals. Go with either the vector form, so I'll put a star on that, or the IJK, the unit vector form. All right, so just because I know where this story ends, I know what we're going to be using this for. So you're better off in either of those two forms. Right? If you slip and accidentally, write it in x equals y equals z equals on a test, I'm not gonna lose my mind and take off credit. Right? But just try to stick with one of these two forms. All right. So the line equation would be, so x of O, 1. Now it's going to be plus TA, right? The A value is 4. So plus -4 times T, so minus 4T. Y sub O is 4. That's going to be plus 1T, so plus T. And Z is -2 plus 2T. All right, so it's really, really not too bad. That's the equation of the line, which we'll call L. Call it L unless you have a conflict. Like you've already called something else L. Like the next one we'll do right below this one, so I'll call that one M. Generally when we're naming lines, unless you're told what to name them, we start off with L and we work our way down the alphabet from there. All right, so another look, P sub O. Just pick one of the 2 points. Doesn't really make a difference. I'm going to use, I'll use Q in this case. I'll use a colon here. So Q is going to take on the role of P sub O. I just want to show you that it's going to work no matter how you slice it. All right. V again is the displacement between our P sub O and our P sub 1. All right, but in this case, I'm going to end up overusing colons here, but that's all right. If I'm calling Q my P sub O, then it must mean that I'm going from Q to P. All right, could have gone the other way. Like I said, I want to show you that it's going to work both ways. All right, so Q to P is the displacement 2 minus 3 -1. 1 minus -1 is 2. 4 minus 3 is 1. All right, and so these will be my A, B, and C values. All right, so then when it comes to my equation, M is going to be, well, we're starting off at 3 minus T, negative 1 times T. So then negative 1 plus 2T, and then 3 plus T. And those are my equations. Well, it is my equation, but they're an equation made up of equations. So what I'll do is I'll take you through Geogebra real quick and show you how this this checks out. So you want a couple of things. One, you want to make sure that you're able to check your work, but also you want to kind of make sure you have the concept of graphing parametrics on using technology down pretty pat, right? Now these are in 3 space, so we're gonna have to use Geogebra for this, all right? So I'm gonna bring that up. I'm gonna get it ready, and then I'll bring you over to that. Show plane, get rid of that. I'm not gonna bother with labels this time. All right, so I'm going to stop that share, and I'm going to start this share. All right, so I want to graph both of the lines, but I also want to graph the points. All right, so I'll start off with the points. My first point was 1, 4, negative 2. All right, my second point was negative 3, 5, 0. All right, so they're floating out there in space, one here and one here. So we got that. That's perfectly fine. I can move the screen around, but I think it's visible enough. So now I just need the actual line. Now the line better go through those points, otherwise I screwed something up. All right, so curve, to get a parametric, no matter whether it's 2 space, 3 space, or 10 space, it's the function curve. It's 1 minus 4t, comma, 4 plus t, comma, negative 2 plus 2t. Now, it's not just going to graph it without you telling it a couple of things. You got to tell it what the variable is, and you got to tell it what the domain is, or where you want it to start graphing and where you want it to stop graphing. Negative 10 to 10 is usually a good place to start, and then you go from there. So that's what I'll do. So negative 10 to 10. All right. So then it'll graph the line, but it may not graph it where you want it to, right? But you do want to kind of, because Geogebra being what it is, sometimes you have to zoom out a little bit in order to see it, and then rotate it around it. Then you can get where you need to go. But if you're not sure, you can dial up these values to something, instead of negative 10 to 10, you can make it like negative 20 to 20. But we got what we needed out of this. All right. So then what I want to do is I want to graph the other one and then see where that's going to take me. All right. So let's pop that information in, or I'll pop that information in and you can observe. So 2, 1, 4. I'm not really concerned with their labels, the labeling from the question. I'm just going to go with what I have here. 3, negative 1, 3. So I got those other 2 points just kind of floating around in space. Just making sure I type them in correctly. They are. Okay. So now I'm going to type in a new curve, brand new, fresh looking curve. 3 minus t, negative 1 plus 2t, and 3 plus t. Now, again, what's the variable? T. Where is it going? negative 10 to 10. Looks pretty good. Looks like it goes through the points that I want it to, here and here, right? Also, you could see that we're looking at two lines that are not parallel to one another, or at least they don't appear to be parallel, but they also won't intersect, right? So two lines that are not parallel in two space would intersect. You know, it's either parallel or they intersect. Here, we're getting two lines that are not parallel to one another, because they're not going to be equally distant from each other for all values of t, but they're never going to intersect. Those are what we call skew lines, right? So I'll make a little note of that in the notes. I'll bring us back to the notes first. I hit the wrong thing. Folks in the living room are going to be like, I was watching that. Oh, all right, so L and M are skew lines because they are not parallel, but they do not intersect. All right. None of the questions asked us that, but it's stuff that you're going to need to know. So why not start becoming more familiar with that now? All right. The second technology assignment deals with parametrics in space, specifically Bezier curves, and I have videos posted on how to walk. You know, I was going to say how to walk through it. No, walking you through it. Videos posting that walk you through the assignment. So definitely take a look at those. But you'll see a lot of familiarity, a lot of similarity between what we're doing now and that technology assignment, which is really the whole point behind technology assignments. Kind of force your hand, make you do the things that I think are important for you to understand the material, right, conceptually. So moving on, and this page is where we're going to end tonight, because after that we get into distance between points of plane. We kind of shift topics a little bit, but what we're looking at is again writing the equation of a line, but then determining whether the two lines intersect with one another. Right, so there's a lot to unpack here, but before we really get too hot and heavy into this, what we can do is come up with the equations, because they tell us it's going through a point which we can now designate as x sub o, y sub o, z sub o, and it's parallel to the vector that's given here, so we call that ABC. So just making sure I'm still recording. So I can come up with very easily my set of parametrics for this line. So 3 minus t minus 1t, comma 1 plus 6t, and then 4 minus 3t. All right. They, I believe, if I'm reading my own diagram correctly, / diagram I stole from the internet, designated this as line L. And so we have an equation. Now we could go through the process of checking it, and we will in a little bit, but I think we'll hold off on that until we absolutely have to. right? For the second one, we have 2 points, right? So I need to come up with a parallel vector, right? So we'll call the first one, yeah, they didn't call them anything. So we'll call the first one the P sub O. Oh, that's not a pen. And the second one I'll call P sub 1. So V is equal to P sub O, P sub 1, the first point after my initial point. 5 minus 1, 4. Negative 2 minus 1, negative 3. 7 minus 2, 5. All right, so those are my ABC values. And this one will be my X sub O, Y sub O, Z sub O. All right, so you got a little bit of an issue here. It's nothing too crazy, but I'm going to make a slight adjustment here in the way I write the equation. All right, so I'm going to call this M. That's not the adjustment. If only. We're going to have 1 plus 4. I'm going to use S, all right, instead of T. All right, we're going to use a different parameter here, all right, because T represents something for line L that it may not necessarily represent in line M, right? So we're going to create, it's going to be a parameter, but it might not follow the same rules as the parameter in L. And we have to allow for that, right? So 1 minus 3S, and then 2 plus 5S. All right, so S is a parameter not equal to T. I mean, I suppose it could be equal, but we can't make that assumption, all right, going into the problem. It might turn out that it is actually equal to T, but that's an assumption that we can't make, right? And it has everything to do really with the fact that we don't know the circumstances that are allowing us to get from P sub O to P1, right? So in this case, I'll make that a P sub O. I'll take that as a typo. Right, so we're going from P sub O to P1, assuming that I labeled my diagram consistently with the points. Hit or miss on that. But if we're operating under that assumption, we're making, and again, perspective is part of this too, so it's kind of a little iffy, but this looks like we're moving in the negative direction to get from P sub O to P sub 1, right? That's fine, negative, and maybe there isn't any real significant change in the XY values. I'm sorry, the Z values. The XY values might be the only things that are changing, right? But in the second case, the movement to get from my first point to my second point, it looks, I mean, we're operating on the assumption that this is even remotely to scale, but the movement to get from the first point to the second point, so again, another piece of O, piece of 1, substantially different, all right? Longer, maybe, but again, assuming it's to scale, to some reasonable scale. It's also indicating a massive increase in Y, a comparative massive increase in Y. So to get from one point to another, a lot of different things needed to happen. Now, the fact that they are going from one point to a second point means that it is following a parametric model, but I can't make the assumption that T is going to be the same constant multiplier for one function as it is for the second one, right? So we designate the equation separately using a different variable. So then the big question would be, well, why didn't we do that on the previous page? It's not so much that we need to do that in all cases. It has to do with the fact that we're about to address the idea that these two lines may intersect with one another. right? So when I'm looking for the intersection between the two lines, that's when I want to make sure my parameters are unique, right? In the previous question, it didn't really matter, right? Because I wasn't comparing them to one another, right? So now what I'm going to do is I'm going to find the intersection between L and M. Well, I got the and symbol. I just forgot to write the L. That's funny. All right. The way we do that is by setting each corresponding component equal to one another. All right, so 3t, I'm going to set it equal to 1 plus 4s. I think I said 3t, I meant to say 3 plus t. I'm going to use my writing tool here. Three minus t, actually. Geez, this is getting fun. Then we have 1 plus 6t, 1 plus 6t, and 4 minus 3t. Just so I don't have to keep scrolling. After that last scroll. 1 minus 3s, 2 plus 5s. All right. And so what we're going to do is we're going to get each of these equations in the standard form for linear systems. And standard form for everything. So I'm going to get the variables on the same side and move the constants to the other side. All right. So this is going to be 4s. Do a different color there. 4s plus t is going to be equal to 2. Then I'm looking at negative 3s minus 6t. Looks like it's equal to a clean 0. That one you could solve pretty easily for s in terms of t, but we're going to use a different approach anyhow. So it's better just get it in this form. All right, 5s plus 3t is going to be equal to 2. We only need 2 out of the 3 of these equations here, because with a system of equations, you only need 2 equations if you have 2 variables. All right, but we have 3, so we'll use them all. Now what I'm going to do is I'm going to strip this down to just the coefficients. All right, so this is the subject of the video, of one of the videos I sent on solving linear systems using matrices. All right, so definitely take a look at that video and drop a like on the video to show your support, et cetera, et cetera. But it gets at the justification for why I'm allowed to do what I'm about to do. All right, so 4, 1, 2, negative 3, negative 6, 0, 5, 3, 2. All right, so this is a matrix, and what we're going to do in a linear algebra class at some point, especially in my classes, you have to demonstrate that you would be able to do this by hand. Fortunately for you, this is not a linear algebra class, so you don't have to do it by hand. We're just using the tools at our disposal. All right, so reduced row echelon form is what we're looking for. What that'll do is it'll convert, well, convert's a poor word to use, but it's really just telling us, clear all. It's really just going to tell us what the simplified set of coefficients would be for the system of equations. All right, so there's a whole lot more to it than that. That's why there's an entire course on linear algebra. But for now, that's a good working definition. All right, so new matrix, we're going 3 by 3, 4, 1, 2, -3, -6, got the 0, 5, 3, 2. So now lock that in, and then you just select the ref function, right? Bottom left-hand corner, ref, type in the A. You get that mamma jamma right there, all right? Tap on that little fraction icon, and you get some more pleasing looking values, all right? So one, if they exist, sometimes they're just nasty decimals, and you're just stuck with them. So 1, 0, 4 sevenths, 0, 1, -2 sevenths, and then 0, 0, 0. So what we're able to do here is take this information, because again, if we're using as our working definition that this is a simplified set of coefficients for our system of equations, then what that tells us is that, and again, that's an oversimplification, but it's good enough for what we need. It's telling us that this first equation would correspond to that first set of coefficients. The second equation with the second set of coefficients, and the third equation with the third set of coefficients. But you can see that it's all equal to 0, so that's going to be kind of a moot point, that last one. All right, but what I can write is 1s plus 0t is equal to 4 sevenths. 0s plus 1t is equal to -2 sevenths. And then 0s plus 0t is equal to 0. All right, so again, just my color coding here. That tells me that s would be 4 sevenths, and t would be equal to -2 sevenths. Now that's a pretty significant outcome here. It's just you don't necessarily always realize the nature of the outcome until you do the work and come up with, okay, well, what are the equations going to give me when s is equal to 4 sevenths and when t is equal to -2 sevenths, right? But what it's telling us specifically is if my first equation has a t value of -2 sevenths, that's going to put it at a specific coordinate, right? It's going to put it at a location on a graph. Now, if I pop in a 4 sevenths in my second set of equations, my second parametric, that's going to put me at the same location, right? So it's showing that there is an intersection, right? We do need to know what that intersection is. Now here it's just saying determine whether they intersect. So it's sufficient to say that the two lines intersect, right? Because we got a solution. But I would want to know where, at what, at what set of coordinates, right? So a couple of ways you can handle that. One way would be the old-fashioned way. Take your, it doesn't matter which one you use. Take your t value, plug it in for t, take your s value, plug it in for s, and then go from there. You do that. All right. I'll just plug in the s for the s because at least it's got a positive value there. All right. So let me I'll clear all. Maybe I didn't want to do that. I don't know. So 1 plus 4 times 4 sevenths in fraction form. We got 23 sevenths. That would be the first piece. Then 1 minus 3 times 4 sevenths. Again, decimal, but that amounts to negative 5 sevenths. And then the last one, 2 plus 5s. So 2 plus 5 times 4 sevenths, 34 sevenths. All right, so I guess I can get rid of these parentheses. So that's where the intersection would be at those coordinates. All right, and we could verify it by popping in the negative 2 sevenths into the other equation, but I'll just do it for the first one just to verify. 3 minus negative, what was it, negative 2 sevenths, so negative 2 sevenths. And you get 23 sevenths. So it worked for the first part, the first component, so there's no reason to doubt that it's going to work for the other components. Right. So, but what I'll do instead of just verifying it point by point is go over to Geogebra and see what the intersection ought to look like. Right. So let's do that. I'll show you, and this will be the last thing we do because it has to be. All right, so get my points in. Well, actually, I don't even need my points. I just want the lines. So curve 3 minus t, comma 1 plus 6t, comma 4 minus 3t, comma t, comma negative 10 to 10. Zoom out. Make sure that you have a sufficient amount of line showing. You know, we got a reasonable amount of line showing here. All right, so my second curve, we're talking 1 plus 4s, comma 1 minus 3s, comma 2 plus 5s, comma s, comma negative 10 to 10. So there's my other line. And you could see that it accepted the s's, so that's good. It does appear that there's an intersection, 2 ways to handle this. One would be to simply type in intersect. All right, A and B are the 2 things we're looking to find the intersection between. Oh, because I use, oh, that was weird. Yeah, because I used T and S, that's not going to work in this case. I'd have to use T's. That's fine. What I'll do instead is I'll just type the coordinate in. .34 seconds. All right, just wanted a quick look anyway to make sure, and it does appear that that is the intersection between the 2 lines. All right, so satisfaction of a job well done when it shows up on Geogebra, and so then we know what we got. We know what we got when we get it. All right, so what you can do, what I'll do is I'll bring you back one last time to the iPad, just to show you which problem I want you to tackle. I mean, it'll be pretty obvious when you see it because it's like, well, there's only one left. So just tackle this problem for homework. So you got a couple of starred problems that you're going to look at, but nothing too crazy. What I'd like you to do though is take a look, and I'll send this out on a remind. Take a look at the videos walking you through the tech assignment. All right, I made them last year, for this course, you know, so with the idea that I'd be able to use them over and over again. I tried to keep them relatively short. They literally walk you through the entire assignment, right? So if you follow those videos, then you'll be in good shape, right? All tech assignments are due the date of the unit test. So that, you know, whatever that date is, I think it's the 4th maybe of November. That's when that tech assignment will be due. All right, so I'll stop the recording.